Hi, in this video, we want to take a look at the normal distribution. Okay, in statistics, this is by far the most frequently used distribution in statistical modeling. I mean, by far. The reason for its ubiquity all over stats is because we use it to model sample averages and sums. Okay, so we can use the relationship between sample averages and the normal distribution to also model sample sums by treating the number of observations as a constant. Okay, so if I have an average, if I have like a sum of observations, it will be approximately, under certain assumptions, approximately normally distributed. Now, why is that? Well, it's because things tend to average out when I have a lot of observations. If I have an extreme value, large or small, if I have an extreme value, then it kind of gets diluted out as we average things out overall, as I get more and more data points, because data tends to be around the central tendency. Okay, so now something to think about is that events that occur from extreme events tend to be skew right. All right, so if you think about item failure of something being dropped, so just item failure in general, but for example, as being it breaks because it was dropped, that was an extreme event. So like things breaking are usually not normally distributed because they come from extreme events. Anytime you have an extreme event resulting in your observation, usually that is not normally distributed. That will be probably skew right. Now, events that arise from averages, sums, composites of variables, and linear combinations tend to be approximately normally distributed. Now, I'm skipping a lot of assumptions about the need. There needs to be like other things theoretically that need to happen for us to be able to have all these guys being approximately normal. But it works out in general for most types of data, most situations. Averages, sums, linear combinations, and composites of variables tend to be normally distributed. So this makes it very useful. All right, so there's a little bit more. So notice that I said approximately normally distributed. And I'm saying it tends to be approximately normally distributed. All right, well, I can be actually a little bit more specific. It works out that if I have a sum, an average, or a linear combination of normal random variables where the data is independent, so we have independent observations and each one is normally distributed, then automatically it's going to be normally distributed, the sum is. And so this makes it so that the normal distribution appears in a lot of places. It's useful. Also, it has a lot of theoretical properties so that if it's approximately correct, I can theoretically work out some details that will be approximately correct for the situation I'm working in. All right, so the normal distribution has a symmetric bell curve density. All right, and here is the equation for the density. All right, now you'll notice that I don't have the cumulative distribution function. The cumulative distribution function basically is defined as the integral from negative infinity to the value, and I don't feel like it's informative, so I skipped it. All right, so mu, this Greek letter, is a real number. It could be negative, could be positive, could be zero. It's the population mean, and it is a location parameter for the entire distribution. It is the center of the distribution in terms of average and median and mode. Now, sigma is greater than 0. It is the population standard deviation, and it is a scale parameter. And sigma squared, that is the population variance. Okay, so now something that is very useful about the normal distribution is that if I take a location scale transform of a normal random variable, the output is itself normally distributed. Okay, so if x is normally distributed, excuse me, then for y equal to ax plus b, a and b are any constant numbers, then the expected value of y is equal to ax, expected value of x plus b, and the variance of y is equal to a squared times the variance of x. That is a well-established property. Okay, so that tells us what's the expected value in the variance if I do a transformation on a random variable like that, a linear transformation. Now, when I say linear, I mean college algebra linear. To see this, all we're going to do is we're going to take the density and apply a U substitution. All right, so let's go ahead and say that I want this transformation. All right, so y is going to be equal to ax plus b. And then, well, that means that x is equal to y minus b over a. And now, if I think about the derivative, it's of x with respect to y, it's 1 over a. All right, so I start here. I go ahead and just start with my regular formula. Now, what I'm going to do U substitution. Okay, and after I do a U substitution, I'll see that I in fact get another normal distribution because I'll have the same formula for the density, except I'll have a different mean. I'll have a different standard deviation. Okay, so do my U substitution. I'm replacing x with y minus b over a. Okay, that goes where the x is, so that goes here. Now, remember that when I'm doing a U substitution, I also have to worry about that dx term and the dy term. All right, so this 1 over a adjusts the dx to dy in my U substitution. All right, so now I'll just go through, I'll simplify everything. You'll notice I have a times sigma. I have a squared sigma squared. And then inside here, I have a mu plus b. All right, now if I look at that and I compare it to this, I've replaced this mu with a mu plus b. I've replaced with sigma, I've replaced the sigma squared with a times sigma squared. Here I've replaced sigma with a times sigma. All right, so I see that I have the same structure, density, just with different parameters. So this tells me that I actually have a normally distributed random variable, and this just comes from doing, changing with a constant multiplication and a constant addition. All right, well, I can change any normal random variable by multiplying and adding, and I still get a normal random variable. All right, this gives us the ability to convert back and forth between different distributions as long as they're both normally distributed. Well, you know what? I'm lazy. I want to do things the easiest way possible. So you know what I'm going to do? I'm going to standardize things. I'm going to standardize things because it's mathematically easier. And this is going to be my reference point for all normally distributed random variables. So what I'm going to do, I'm going to set mu equal to 0. I'm going to set sigma equal to 1. And then I'm going to get my normally distributed random variable. And that looks a little bit nice, right? I don't have a Greek mu going on. I have simpler squaring. I don't have as much going on in the fractions. This is an easier equation to work with. All right, so I have the ability to switch back and forth freely. So if I start with standard normal, I can always convert over freely. All right, so now let's take a look at the expected value of a normal random variable. All right, so I can use that expected value equal to ay plus b trick that we have previously to convert from standard normal to any other normal distribution I want. So what I want to do, I'm going to use standard normal as a baseline and then figure out the normal random, the expected value there, and figure out the variance, and then extend that over to any normal random variable. Okay, so here for expected value, I'm just going to go ahead and I'm going to do y times the density, standard stuff, and I'm going to integrate over the entire real line. Okay, so now I want you to notice something. Inside here, what type of function is that? Well, that defines an odd function. If it's an odd function, it means one of two things are happening. When I integrate over the entire real line, either it's 0 or it's undefined. One of the two is going on. Okay, well, let's go ahead and do some integration. Now I notice that y and y squared over 2, there looks like there might be a relationship there, between the, the derivative, right? Okay, so I'll go ahead and take, I'll do the antiderivative. I get 0. Boom, we got the expected value is equal to 0. Now, let's go on to variance. So for variance, I'm going to use the familiar trick of the variance is equal to the expected value of the variable squared minus the expected value of the variable squared. Okay, so I'll go ahead and have y squared times the density and integrate over the entire real line. Now, notice that what's inside the integral defines an even function because I have a y squared and I have a y squared here. It has to be an even function. Therefore, the integral, the overall integral is equal to 2 times the integral over 0 to infinity. All right, so here I'm cutting the integration interval in half by multiplying by 2. All right, so you'll notice that this goes from negative infinity to infinity. This goes from 0 to infinity, and I'm just doubling it. Okay, so now I'm going to check this out. I just do a little bit of simplification, and I've got this integral. Now, we haven't talked about anything looking like this because I've got e to the negative y squared over 2. Okay, what do we do? Well, you know what I'm going to do? I'm going to do u substitution. Now, if you're doing calculus and you have a u substitution and you don't know what to do, ask yourself, what is the biggest pain in the neck? Whatever is the biggest pain in the neck is what you want to do the substitution on. So I view y squared over 2 as being a pain in the neck. I don't like that. That's the most complicated term in this entire thing because it's on the inside of that exponential. All right, so I'm going to replace y squared over 2 with u. Okay, well, that means that 2u is equal to y squared. All right, so I know that this y squared is going to be 2u, and I can also go through and I can solve for y. Once I solve for y, I take the derivative of y with respect to u, and I'm going to use that to do the conversion of dy to du. Okay, so what happens? This y squared is going to become 2u. This y squared over 2 is going to become u. Now this dy is going to become 1 over the square root of 2 u to the negative 1/2 du. Okay. So when I do that, this integral becomes this integral. Now I look at that and I realize, well, that's u to the 1/2 e to the negative u. That's the gamma function. All right, so I'll go ahead and invoke the gamma function. All right, so in the gamma function, I know that I have a special property that if I reduce the variable or reduce the value inside by 1, I factor it out simultaneously so I can reduce things. All right, so here if I reduce down to 1/2, I just multiply the front by 1/2, and it's, and I get the same value by the property with the gamma function. All right, well, the 2's cancel, and so an identity we need to have memorized is that gamma of 1/2 is equal to the square root of pi. So then 1 over the square root of pi times the square root of pi is 1. All right, so therefore the variance is equal to 1 minus 0 squared. Boom, we got standard normal variance. Now, if I want to go ahead and get the expected value or the variance of any other normally distributed random variable, I just use that ax plus b trick. And, or in this case, ay plus b will give it to me. All right, well, that's all I've got for you. Take care and goodbye.